Hi everybody, if you've been following these videos in sequence, you've seen that we've been working on the chi-squared analysis. We started off with a one variable chi-squared. Now we've done some two variable chi-squared, or at least one two variable chi-squared. And now we're going to see what we can do after we found a statistically significant chi-squared value. In other words, we found that this is an unusual statistic, and therefore there seems to be some association between the two variables that we looked at. So of course, generally what we do after a statistically significant finding is we start looking at things like measures of effect size, for one thing, and of course some others depending on the exact analysis. So I'm going to talk just on measures of effect size here and what we can do for our two variable chi-squareds. So of course, if you have a one variable chi-squared analysis, there's no measure of effect size possible because there was no effect there. You weren't looking at the effect of one variable on another, you were just looking at the patterns within one variable. So therefore no measure of effect size. Now there's something sort of analogous to it in some ways anyway, the standardized residual, which we covered in a previous video. However, when you have two variables, now you can start to assess the degree of association between those, or what essentially would amount to be effect size. Now, of course, there's some different ways of measuring effect size for chi-squared analyses. Some of them seem a little more appropriate than others depending on the circumstances. Some of them are preferred among statisticians among some others, and so I'll try to talk about each of those elements here. Some of them are important for a 2x2 chi-squared, and some of them would be more important or more preferable for a larger design, such as a 2x3, a 3x8, 4x3, whatever. There are lots of ways that you can do that. So let's just start with the simplest kind of two variable chi-squared design for a 2x2. And of course, I'll be referring to the statistics and the information that we already obtained from a previous example. All right, so many statisticians believe that the odds ratio is probably the best measure of effect size for a 2x2 design. It doesn't make a whole lot of sense using any larger tables than that, however. So I'll explain what that is, and I'll refer to a previous example, of course. So the odds ratio is simply the ratio of the odds of one of the levels of the variable falling into one of the other level compared to, one of the other levels of the variable. Okay, I'll walk you through that example here. But then we'll see the odds ratio. So it's a little confusing to actually interpret. I'll give you an example here, however. This is one way of thinking of it, however. It's the odds of a given level of the first variable occurring in a given level of the second variable. And it's the ratio, this is where the ratio comes into, the odds ratio, that to the odds of that same given level of the first variable occurring in the other level of the second variable. So again, that probably doesn't make a whole lot of sense now. That's what I mean by the odds ratio. Is a little difficult to interpret, but we'll try this out, okay? Let's use that example that we used it with the medication and the placebo and heart attacks from the previous video, and we'll walk you through how to do this. Okay, if you don't remember this, what we did is we had somebody named Dr. K. They were testing out this new medication to see if it prevented heart attacks among high-risk patients compared to a placebo. And so this is how the data looked in that previous example. There were 160 people, of course, and each of them fell into one of these four cells, of course. And this is a 2x2 design, obviously. Okay, so once again, you recall that this was statistically significant. We're going to need this information for later. So again, the chi-squared value with 1 degree of freedom, we had 160 observations of the variable, and our chi-squared value is 4.42. So this is where I'm getting all of this. If you don't recall how we arrived at this, you can see the previous video. So first, what we need to do is calculate the odds that someone will have a heart attack with the placebo. So the odds of this occurring to that occurring, okay? Then we'll do the same thing for the people receiving the medication. Then we're going to look at the ratio between those two odds. That's basically it. So it's not very difficult to compute. It's a little challenging to interpret, however. All right, yeah, so we'll do this now. Of course, here are our data. We've got this. So first we figure out the odds of having a heart attack with the placebo. So of course, certainly we just take the odds of having a heart attack, or I'm sorry, we take the proportion of people who had a heart attack with the placebo. We divide it by the people who did not have a heart attack with the placebo. That gives us the odds of having a heart attack after having received the placebo. In other words, the odds are 0.40. Okay, then we need to calculate the odds of having a heart attack with the medication, which of course is the same thing, 12 to 68, which of course gives us the odds of 0.10. Now all we do is we take to determine the odds ratio is we take the ratio of that first odds to those second odds. Okay, and basically that looks like this. 0.40 divided by 0.10 gives us the odds ratio. Okay, the odds ratio is 2.22. Now the interpretation again is rather difficult, but what we're saying is that the people who took the placebo have 2.22 times the odds of having a heart attack compared to those who took the medicine. That is not the same thing as saying they are twice as likely to have a heart attack. That's not it, because we're talking about odds, okay? So it's 2.22 times the odds of having a heart attack. Now, that sounds like quite a bit. And this is where we run into one of the inherent tricky things about effect sizes, using words to describe how big of an effect there is. Now, in an instance like this, where we're talking maybe life and death, because a heart attack is potentially fatal and a lot of people die every year of heart attacks, this seems very large to me. I would look at this and say, wow, the placebo really wasn't helpful in preventing heart attacks, which of course it wasn't intended to. This medicine seems to make quite a difference. I mean, this is many lives that we're looking at, okay? So if we can save even just a few lives using this medication, who's to call that a small effect, right? Who's to call that even a medium effect? So those words get a little tricky there. Anyway, so that is the odds ratio. Very quickly, you can see how to do that. And again, as I say, most statisticians prefer this method for 2x2 chi-squared analyses. Let's look at another one, however. Another common one that you'll see for a 2x2 table is called phi. Phi, of course, is a Greek letter. This instance is the lowercase Greek letter of phi. So as I said, you'll use these for 2x2 chi-squared designs. However, you can calculate it with really any chi-squared chi-squared design that has two variables or more. Yeah, I think that's true. You can also use it with more than two variables. It starts to get very difficult to interpret, however, if you have a larger than 2x2 table, however. So if you have a 2x3 table, it turns out what happens is now phi can take a value on that is greater than 1. And so that gets confusing to interpret, but it is technically still possible. Now, it's very similar to a correlation coefficient in that it ranges between 0 and 1. Of course, a Pearson correlation can also be negative between 0 and 1. However, phi can only be positive, of course, as we'll see in the equation. So with 2x2 tables, it can really only range between 0 and 1. That's rather important. It's very simple to calculate as well, as you can see here. So what we're doing here is phi is equal to the square root of chi-squared value. That's the one that you actually obtained, the value that you calculated with your data. You just take that same chi-squared value and you plug it right in here. And this is, of course, the total number of observations that you had. So let's take a look at how to do that using our previous example. Of course, as I showed you previously, these were the results from our chi-squared analysis that we did. So all we're really needing here is the 160 value for our observations, number of observations, and of course 4.42 was our chi-squared analysis. Therefore, this is what it looks like. Phi is that. We input our chi-squared value. Notice here, we're not squaring it again. Some people tend to do that. They go, oh, well, you're supposed to square that. But no, it was already squared, right? That's the chi-squared value. So you simply put it in there, and as you see, we're going to take the square root, so it would be silly to square it again. Anyway, you take 4.42, you divide by 160 to get, of course, 0.027. The square root of that is 0.17. Now let's get to interpreting phi. Phi, we interpret essentially just like a correlation coefficient as long as we're using a 2x2 table. Again, because if you have a phi value that is 1 or larger, now it starts to get because you can't have a better than perfect association, right? So again, that's why it's tricky. But these are the same metrics that we used as far as the words to call it with the strength of the phi value. This, of course, is just in a different font. It looks like maybe a different symbol, but it is a lowercase phi. So anyway, if you have a value of between 0.40 and 0.49, of course, we would refer to that as a moderate relationship, a moderate effect size, for example. Now, in this case, we had a phi value of 0.17, so we would interpret that as no effect size. In other words, it's so small that we actually can't say that it's even weak. So again, we see the disconnect here between what the odds ratio basically suggested to us and what phi says, because phi says, yeah, that's a very small effect size. In other words, it doesn't seem to make a big difference if you and you're getting a heart attack if you have the medication or the placebo. But of course, if we're looking at the odds ratio, it seems, gosh, I mean, the odds difference there is pretty important. And if I were maybe at a high risk of having a heart attack, it would sure seem like a good idea for me to take that medication. Even if we're not talking really big differences in numbers, every single one of those differences mattered. Okay, so there we go. All right, one last one we'll look at. The last one we'll talk about is Kramer's V. Kramer was the name of the person who came up with this. I believe he was Hungarian or something like that. It doesn't matter for our purposes. Anyway, Kramer's V is almost exactly the same thing as phi. However, phi is used for 2 by 2 tables, and Kramer's V is adapted so that it can be used for larger tables. For example, if you have a 2 by 3, a 3 by 4, a 7 by 8 table, whatever. It doesn't actually matter. In fact, if you use Kramer's V with a 2 by 2 table, it's exactly the same thing as phi, as you'll see once I show the equation here in just a second. So when in doubt, you could go ahead and use Kramer's V, and it doesn't hurt anything. Here's the equation. Again, very simple to calculate. It's just a little more complicated than phi, of course. Phi just divided by n, as you recall. However, v, in order to adjust itself to this to the larger tables, takes the lesser of the rows or columns, and then subtracts 1 from that and multiplies it by n. So in other words, if we had a 2 by 3 table, we would take the lesser of the rows or columns, and if it's 2 by 3, then we have two rows and 3 columns. So we take the lesser of that. 2 is less than 3, so of course that would be 2 minus 1, which is of course 1 times n, and so now we have what is essentially phi. It's exactly the same thing. However, if you've got a 3 by 4 table, of course, then this would be 3 minus 1 and 2 times n, and so on, okay? Now, one important thing is that there is also a problem with V that's been discovered by somebody named Bergsma. Bergsma is another statistician. Doesn't really matter. However, V tends to be biased with small samples or large tables, and so it shows this. It's a subtle problem, but it is a problem. So if you have large tables or relatively small sample sizes, or especially a combination of both, there is a correction for it. I review that in another video on this playlist, so you can take a look at that if that ever is something that occurs to you. All right, of course, quick summary. Measures of effect size are very important to compute for any statistics. The American Psychological Association, of course, requires that you report measures of effect size whenever you do report statistics, unless it really doesn't make any sense to do so. For example, in a one variable chi-squared analysis. So it's important information because especially when this heart attack kind of information comes up, you want to know, well, then should I take this medication or not? And how big of a difference is it likely to make? Okay. So generally, we do prefer odds ratios if that's appropriate for your design. Of course, they're a little complex to interpret. That's somewhat frustrating. Phi is a great idea also. It's similar to a correlation. It's essentially a correlation between these two binary variables, of course. And so again, a little challenging to interpret, but it works fine. And then Kramer's V is analogous to phi. It's almost the same thing. It's just adjusted for smaller ones. But of course, be careful of that bias that it has. Okay, that's it for this one. See you next time.